Okay, you can see my screen, right? Okay, good. So remove this. Okay. Okay, so good evening. So welcome to the week 4 problem solving session of theory of computation. So a few things due to the requests in the last week. So what we'll be doing is we'll be slightly modifying the way in which I'll be conducting the problem solving session. So last time, as Suresh pointed out, I will be solving some of the questions that you know arose in that were there in the assignments. Okay, and only for those assignments whose deadlines have been over, okay, or whose solutions have been released already, since they do not explain what the solutions behind the options are. So I'll be explaining those questions and the reasoning. At the same time, I won't do all the questions. I'll just handpick a few of them, and half of the session will be dedicated to this. Okay, solving the past assignment questions, and the remaining questions will be related to the current week, so that you get some help in solving the questions for the next week. Okay, so let us begin. So this was assignment 1. Okay, so let me shift this. So this is assignment 1. Today I'll be doing assignment 1 and 2. Okay. So this is from assignment 1. So here's the question. So define a non-reflexive finite automaton, or NRFA, as a DFA with no self-loop. Okay. That is, delta of QA is not equal to Q for any state Q and symbol A. Now let NR regular language be any language that can be recognized by an NRFA. Which of the following statements regarding NR languages are correct? So the first question is any non-reflexive regular language. Okay, NR regular language is a regular language. Any regular language is an NR regular language. There are regular languages which are not NR regular. There are NR regular languages which are not regular. So you need to compare NR regular languages and regular languages. So NR regular, meaning DFA has no self loops, and regular okay, regular languages are just simply DFAs, and they can have self loop. Okay, regular languages can have self loops. So the question is, any NR language is regular language? Let's ask that question. NR is contained in, let me call it RL, but this is regular language. Okay. Is NR contained in RL? That is the question. Well, in other words, I could say that let me call the DFA with no self loop as NRDFA. Okay, let me call it that. So given an NRDFA, can I construct a DFA, a simple DFA, accepting same language? Well, but this is trivial. Why? Because see, NRDFA is simply a DFA which looks like this, something like this, without self loops. Self loops are not there. So NRDFAs are DFAs. This satisfies the definition of DFAs, even though they don't have self loops. NRDFAs are DFAs trivially. Okay. Next, NRDFAs are DFAs trivially. Now the question we ask is, are regular languages contained in NR? Okay, non-reflexive regular, let's call it NRRL. NRRL is the question. So given a DFA which has loops, possibly given a DFA which has loops, possibly, can you convert it into a DFA that need not have loops? That is the question, right? Well, remember now that I don't need to construct a DFA. It's not necessary. I just need to okay. I can construct a non-deterministic version. Okay. So what I can do is I can simply, if there is a loop on A, I'll replace every self loop. I'll replace every self loop. Okay. I'll replace every self loop by something like this. If there is a state like this, okay, then I'll do, okay, and let's say B and C, okay, then I'll just do an epsilon transition to another state A prime and then do A. I'll just replace each of these occurrences. Each of these I'll replace with this block. What happens then? Or I can even do vice versa. Or I can even do vice versa. That is, this is more intuitive actually. If there is an A, then I do epsilon. So as the DFA sees an input, okay, and it loops on the self loop several times, in the this NRDFA, the construction that they give, what will we do? We'll just get in here into the state, and we see an A, we see an epsilon, because epsilon is always there between two symbols, right? We see an A, we see an epsilon, and this acts as a loop. This acts as a self loop. But if you notice that if I replace every self loop in the original DFA with this particular block, then there are no self loops left in the DFA, right? Yeah, in the NFA, right? So then the language is NRRL. I can replace every self loop with this particular block. Therefore, what are your answers? Your answer is that any NR regular language is a regular language, and any regular language, okay, any regular language is an NR. We showed both the containment. Firstly, we argued that, okay, if your DFA does not have self loops, it is still a DFA. So it is trivially regular, and it is always regular. But the other direction, if your DFA has self loops, but you want to make a DFA that does not have self loops, you just apply this particular gadget, this particular block in place of each self loop, and it will work. And then your resulting NFA will not have any self loops. Okay. I hope it's clear. Okay. Okay. To those who joined just recently, I have changed the format of the sessions. Okay. I'll be discussing past assignments. Today I'm discussing assignment 1 and 2, questions from 1 and 2. And the other half of the session, I'll be discussing some things regarding to this week. Okay. And yeah. Okay. So let's move on to the next question. Okay. So, okay, this is a huge question, but bear with me. It actually does not mean something very complex, but let's see. Let M, okay, Q sigma delta, Q naught F, okay, so on. M is a finite automaton. Okay, it is a DFA. And we know this particular fact. Okay, this is a known fact that if, I have a string which is W1, W2, and so on until Wn. Okay, if there is a sequence of states, okay, such that R0 to Rn, such that R0 equals Q0. What is Q0? It's the start state. Such that beginning from the start state, and on reading the next symbol, I'm moving to R1. On reading the next symbol from R1, I'm moving to R2 and so on. This is what it represents, right? Ri, on reading the next symbol, moves to Ri plus 1 and so on until n minus 1. And at the end, what? Rn is in final state, the set of final state. Rn is in F. Then what? Then we say that the string W is accepted by the automaton. Right, this is a standard definition. There's a sequence of states where at the end I reach the final state. Okay, there is a sequence of states at the end of this the list. Okay, this is R1, R2, and so on, and until Rn. Okay, if I reach Rn and Rn is a final state, then this is accepted. This is the general definition of a DFA. Now, what is the change here? Okay, a pass-through finite automaton or a PFA is identical to a DFA except for the following modification to condition 3. Which is condition 3? This, the final state condition. What it says is Ri is in F for some I in 0, 1, 2 and so on till n. So what does it mean? It means this is not the only case when I accept a string. If it so happens that on reading a string anywhere in the path, okay, anywhere in the path, I encounter a final state, then accept. Getting it? If let's say the input was A, B, A, C, okay, B, B, and let's say on A I move to this, on A I move to this, on B I move to this, and on A I move to this, and on B I move to this, and so on. Okay, notice that if in my normal standard DFA, if this had happened, okay, and finally I landed to this state, but this state is not a final state. So this string would be rejected in that case, in the normal DFA. But this is a special type of DFA which we are calling what? PFA, or pass-through finite automaton. As long as even one final state is encountered, for example here in its path, one final state is encountered. It could be more than one, remember, okay, it could be like this, okay, it could be more than one. Then I'm good. This is accepted. The string is accepted. Okay, I hope you noted the difference. Furthermore, okay, what is an exact finite automaton or EFA? Is identical to a DFA now, except for the following modification. Again to condition 3, this is the condition. R is in F for exactly one I in 0, 1, 2, 3 and so on till n. What does it mean? If this is the path, there are two final states in the path. This is not good for me. I want exactly one. So something like this would be accepted. Then accept. Clear? I hope the idea is clear. For example, if it's like if you're exact, okay, this is for exact and this is for pass-through. For example, if in exact DFA, okay, if you encounter this on an input, you go through this path, you see two final states, then this means string is not accepted. To accept, you need exactly one. You need exactly one final state. Okay. For example, here there is exactly one final state. You'll accept it. But remember that this condition was allowed in the pass-through automaton. In pass-through, at least one final state is encountered in the path, then you accept. Finally, to recap, the normal DFA, the standard DFA that we all know about. Okay. What is the acceptance condition? Any number of final states is okay in the path. I will allow it. Okay, I'm not going to reject it. But When do I accept? I accept only if the last state in the path is a final state. Okay. Okay. So I hope, okay, the definitions are clear now. Now let's look at the questions. Okay. Question says, which of the following statements are correct? Any P regular, okay. By the way, it says, okay, let P regular language be any language that can be recognized by a PFA, and irregular language be any language that can be recognized by an EFA. Okay. So this corresponds to P regular language, and this corresponds to irregular language, exact regular language. Okay. Now we are saying any P regular language is a regular language. The question is P regular language? This is what it is asking. Also regular. Is any P regular language also regular? Okay. Or in other words, okay, what we can say is, for any pass through automata PFA, can we design a DFA or NFA accepting the same language? If you show this, then it means that any language here is contained here, no? Because if you have a DFA or NFA for it, then it means it's in regular. It's a regular language. Okay. So now look at it carefully. A pass-through automaton, for a pass-through automaton, this is somewhat what it looks like. And accepting, this is acceptance on a pass-through automaton. And what is rejection in a pass-through automata? Well, this is rejection. Here, at least one final state, no final state in the path in a PFA. Now, can I reduce the size? Oh, okay, I can't. Okay, now look at a DFA. What does acceptance in a DFA look like? It looks like this. This is what a acceptance in DFA looks like. We always end in the final state. What does rejection look like? Well, rejection need not be all non-final states. You can have final states in between. Something like this is allowed. But this is important. At the end, you are in a non-final state. So question is, can you convert this model to this model? So let's look at the acceptance. PFA accepts when at least one final state is encountered. DFA accepts when exactly one, when there could be final states in between also, but this is the important thing. Okay. This is the important thing. The end state. So what I'll do is simple. If this is my PFA, okay, if this is my PFA, what I'll do is, as soon as I see the first final state, I'll cut it off. Okay, I'll cut it off. If I cut it off, then it is as good as, and this is treated as my final state. Okay, I'm being very hand wavy here. Okay, but if this is treated as my final state now, then this is working like a DFA only, right? The first final states that I see, okay, there could be more here, but the first final state I see, I'll cut it off. So how do I achieve this? I will, to each final state, remove all outgoing transitions. Okay, this is the final state. Okay, then I'll remove all outgoing transitions. So I want to cut off, because I want to end wherever the first string was seen. Okay, now next what will I do? Yeah, so but what happens if I cut off? Well, it was accepting a string before, okay, but my string doesn't end here. No, my string keeps going. It's supposed to keep going on. It's supposed to keep going on. I have it still needs to read and move to other states, right? But it's not totally necessary. What I'll do is an add self loop. Right. I'll just add a self loop on all symbols. So now what happens? As my input is coming to the PFA, as soon as I see the first final state, I have removed all transitions here. This is removed. So I'm stuck at this final state. Getting it? So what happens? This becomes a DFA. Think about it. Why is this a DFA? Well, if some input, okay, let's say W is in the language, then what happens? There is at least one final state in path of the PFA, pass through automaton. By definition, at least one final state will be there. Okay, at least one final state will be there. And since at least one final state is there, and by the construction we've removed all all these edges, outgoing edges, computation will loop and end at first final state. But in this computation path, since this was the first final state, okay, since this was first final state, for my resulting DFA, it is the last final state in the path, right? Resulting, not DFA, let's call it automaton for now. Last final state, because after in the path, because it was the first one that we encountered, or I think this is a better thing to show. It is the first one that we encountered, and we stayed here. We stayed here until it accepted. And originally also, since it was already seeing at least one final state, it was already accepting. So now what we're doing, now we've converted into a DFA. It is just stuck here. No matter what you see, whether you see an A or whether you see a B, whether you see a 0 or you see a 1, you're stuck here. And when you finally end in this state, you've converted the acceptance condition basically into a DFA, because this was the last final state you saw. Okay. Now, let's say W was not in the language, then by PFA definition, obviously no final states in path, which means my modification here also did not affect anything, because I was only modifying the final states. Since I did not encounter any final state, automata new modified automata also does not have final state in its path. So the result is still the behavior of a DFA, because what does it mean? Last state in the path is not a final state. Since the last state is not a final state and we are rejecting, it means we've converted into a DFA. Okay. So by this, what do you have? By this, we have that any P regular language is a regular language. How? We took a PFA and showed an equivalent DFA for it. So this is the first option. Is that clear? Okay. Now that's the relationship. So any regular language is a P-regular language. There are regular languages which are not P-regular. There are P-regular languages which are not regular. Yeah. So clearly this is not the case. You cannot go the other way around, because when you look at the PFA, you need to look at least the condition is at least one final state. Okay, but in the DFA you have final state at the end, so it's not possible to make a PFA out of a DFA always. So let's look at these two. Okay, there are regular languages for which are not P-regular, and the next one, there are P-regular languages which are not regular. So basically you are asking, if you have the set of regular languages, this is what we just showed, right? This is what we just showed. P-regular languages is contained in RL. Question is there some strictly, is there a language here which is not P-regular? This is the question you are asking. Okay. Clearly this is also not, there are regular languages which are, clearly there are P-regular languages which are not regular. This is also not an option, because clearly PR is contained in RL. So obviously every P-regular language is a regular language. So this is not an option. So we need to verify this fact. There are regular languages which are not P-regular. Okay. Now here we need to think a little. Okay. PFA means at least one final state encountered in computation path. Right. Here we'll not look at it from a machine theoretic point, we'll look at it from a language theoretic point. Okay. So it means that if this is my computation path, and again there are several final states here, but the first final state is enough for me. That's what we learned, right? As long as at least there's one final state in the path, we are fine with it. And let's just cut off at the first one. So what do you observe? We observe that, oh, okay, if the prefix of the word, let's say if AB, okay, or let's say 001 is in the language, say 001 is in the language, then everything followed, everything 0000 000 001 001 001 anything followed which follows 001 should be accepted by the PFA, right? Because when I saw a 001, it means, and it is in the language, it means there is some path that goes 0, then 0, then 1. Right? This is a start state, 001, and it lands into a final state. This is what it means. right? Or it is somewhere earlier, but let us assume that it lands in a final state here. It means that since now anything that comes after 001, okay, 0000010, 001 and somewhere 0, maybe it landed here or wherever, and 0011 it landed somewhere. But the fact that I have at least one final state in my path means that by definition of PFA I should accept. So you see, right, the PFA accepts nothing but prefixes. If a word is in the language, if a string is in the language, then any extension of that string will also be in the language. Okay. Now let's see. Now this is now it will be clear. Okay. Let my language be 01 star. Okay, let my language be 01 star. What will it look like? Well, it can have epsilon, it can have 01, it can have 0101, it can have 010101, and so on. This is what my language will look like. What will my DFA look like, which accepts it? I have a start state. If I see a 0, then I go to this state. If I see a 1, I go to this state, and this is a final state. Okay. This is correct, right? I hope all okay. And further, if this sees a 1, I'll stay here. If this sees a, oh no, this should not be there. And there will be some dead states. If I see a 1, then here. If I see a 0, then it goes to a dead state. But this is the DFA for it. All of you, I think, agree for this language. Now, let's try constructing its PFA. Let's try constructing its PFA. Okay. Let's do the same logic. Okay. If I have a state, if I see a 0, then I move here. If I see a 1, then I move here. And this is the final state. Well, this is well and good. Okay. 0, 1, 0, 1. Okay, let's just look at 0, 1. Okay. Now let's look at 0, 1. 0, 1. Is it accepted by the PFA? 0, 1. Yeah, there is at least one final state in the path, so we'll accept it. Accepted by PFA. Now let's look at 0, 1, 0, 1. Is it accepted by the PFA? Yeah, well, 0, 1, I already encountered one final state, but let's go on 0, 1. But I encountered two final states, 2 times, but it's fine. This is accepted. You'll realize that, oh, okay, it'll accept all 0, 1, 0, 0, 1, 0, 1, and so on. The problem is in the no case. Look at this string 0, 1, 0. This should not be accepted by the PFA. 0, 1, 0 is not in the language. But I see a 0, I see a 1, and I see a final state. And then I see a 0. I have seen a final state once. And at least seeing a final state, at least one is enough for my PFA to accept it. 0, 1, 0 is accepted by PFA. But 0, 1, 0 is not in the language. Now, how can you say that, okay, maybe there is some other PFA which you can construct for this language? Well, you cannot. Why? Because when you read a 0 and then you read a 1, you are supposed to, in the PFA, you are supposed to encounter a final state. But when you see, then you see a 0, then what should be, by the definition of PFA, you should not have seen any final state yet. Given a string 0, 1, 0, okay, if your string is supposed to be rejected by the PFA, the path should not have any final states. But you had already encountered a final state when you saw this one. So you cannot, so not possible to design PFA. Not possible to design PFA for 0, 1 star. Hence, what do you have? There are regular languages. We know 0, 1 star is regular. We just saw DFA for it. There are regular languages which are not irregular. This is the answer for question 11. Okay. Is that clear? Just let me know.
Yes, sir.
Okay. Good. Others, I hope it's clear. Now, similar flavor, okay? Now we are talking about exact regular languages. Let me recall from the paragraph definition. Exact regular languages are those accepted by EFA, which means exactly one final seat in its path. Right? Exactly one final state in its path. So it'll look something like this. If you are supposed to accepting case, let me write it a bit more neatly. Accepting case. Yeah. Accepting case, it could be any series of states, but there is exactly one final state. Not more, not less. What does rejecting case look like? What does rejecting case look like? Okay. This is a rejecting case. There are no final states, or this is a rejecting case. Where there are multiple final states encountered. Multiple final states encountered. Why is this a rejecting case? For exact NFAs, you need exactly one. Multiple final state means it's bad for me. And we are going to use that fact. Okay. I hope this part is clear. Rejecting case, accepting case in an exact NFA is in its computation path, anywhere I need to have exactly one final state. Rejecting cases, either all of them are non-final, all non-final, or multiple non-final. Okay. First question. Can we show that any P regular language is an irregular language? Can you show that any P regular language is an irregular language? Let's try that. So you have P regular. Is it, okay, let me write PRL. PRL, is it contained in ERL? That is the question. Can you do it? Let's try. P regular language will look like this and several. And I'll do something very similar to what I did before. Okay. I'll just cut off the first final state I see and I'll stop there. Okay, let's try. Again, do the same thing. For every final state, what you do is you remove outgoing edges. Okay, you remove outgoing edges. What did we do before? We removed outgoing edges and added a self loop. No, and we add a self loop. And this is my new final state. So it means that as soon as I saw this state, sorry, this is a bad example. As soon as I saw the exactly one, I got stuck here. As soon as I saw the exactly one, I got stuck here. And as soon as I see the first final state, I got stuck here. And for the PRL, it was enough to see at least one final state. And in the ERL case, I have replaced it with exactly one final state because I cannot move out of this path now. I cannot move out of this point. I cannot visit more final states. So hence, for the accepting case, there is exactly one final state in the path. Okay, fine, good. Now, rejecting case, in the PRL, what is the rejecting case? In pass-through automaton, the rejecting case is when there are no final states encountered at all. Again, when I did this modification, I only modified the final states. I did not modify the non-final states. So it means if I have only if it means I have only non-final states in the path, I will never ever encounter a final state. I'll never ever encounter a final state. And I did not modify any non-final states. So it simply means that it satisfies one of the rejecting cases of EFA, right? That none of the states in the path are final. So this construction works. PRL is contained in ER. Okay. I hope that was clear. So please let me know if you want more time to process these things. Okay. So we have just shown that PRL is contained in ERL. Earlier we had shown this, right? RL, regular contains ERL, contains PRL. This is what we showed. So any P regular language is an irregular language. So as soon as I say this, there are P regular languages which are not regular, this becomes wrong. Now question is between these two. Any irregular language is a P regular language. So the question we are asking is there nothing here? That is what it means. No. Are they equal ERL and PRL? Or is there a language here which is in ERL but not in PRL? So we'll construct this exact language. Let's see how to construct such a language. Now, like I told you in the previous one, if you observe PRLs, it is about, prefixes. No, if you have a prefix, okay, if you accept 101, then any extension of 101, 101, 000, 10, and so on will always be accepted. Similarly, here is the notion. Here we need to look at the machine again from a language theoretic point of view. We realize that we want to do with something to do with exact count. Okay, something to do with exact count for exact regular language. So here's my language. L is all the strings such that W contains exactly 101 block. Okay. Example 11010. something like this. Okay, this is not correct. This is not what we want, but this is good. Exactly one. Claim is that L is exactly sitting here at this point. Okay, that is, it is in ERL but not in PRL. Okay, why? Let us construct an ERL for it, a EFA for it. We'll show that L is in ERL first. Okay, let's construct an EFA for it. An EFA, okay, let's just think of the DFA first. What do we do? We'll see a 1, we'll see a 0, and we see a 1. Then we are good. Right. Now what I'll do is, okay, and here maybe zeros, and here maybe ones, and here maybe zeros. Okay, here, or forget about these things. Let's not worry about these small details. If I see 1 0 1 0, I'll go here. Okay, now let's look at the example. Will I accept 1 0 1? Remember that this is an EFA, it's not a DFA. Okay, let's see. I'm in the start state. 1 followed by 0 followed by 1. I have exactly one final state in my computation path, so this is accepted. Now, next string, let's try this 1 0 1 0 1 0 1 1 0 1 0. This should be accepted, right? This is supposed to be accepted. Let's see, because it has exactly 1 1 0 1 block. So let's see. First I see a 1. Sorry, first I see a 1. Then I see a 1 again. Okay, there should be a self loop here. Then I see a 1 again. Then I see a 0. Okay. Then I see a 0. I'm here. Then I see a 1. I'm here. And then I see a 0. So far, I've seen only one final state. So I'm good. It is accepted. Exactly one final state I accepted. Now, let's do the bad example. 1 0 1 0 1. This is not supposed to be accepted because there are two blocks that are 1 0 1. Let's try 1 0 1 0. Oops, the construction is slightly incorrect. When I see a 0, I should go here. Yeah. Okay. Yeah. Sorry for that. 1 0 1 0 and 1. How many times did I see the final state? 2 times. But EFA, if it sees a final state 2 times in any path, it will reject the string immediately. So 1 0 1 0 1 is rejected, and rightfully so. We want it to be rejected. Then good. First thing we proved L is in ERL. Now L is not in PRL. This we need to show, right? Let's try to show PFA. Try constructing PFA. Okay. Now again, let's do the same thing. This, first of all, if your DFA accepts 1 0 1, it means this kind of structure is present somewhere in your DFA, right? 1 followed by a 0, then you see something, then you see a 1, then finally you accept. This block should be there somewhere, okay, to accept this language, exactly 1. Now, how do you claim that? Okay, for example, let's say I see 1 0 1 1 0 1. Okay, this should be rejected. Right, this should be rejected because there are two 101 blocks. So let's see here. If I see a 1, then I see a 0, then I see a 1. Good. Okay, we are accepting if there is exactly 101 block. But this should not be accepted. So, and let's say like before, I see a 1. Yeah. Again here, if I see a 0, then I come here. 101, 10. And if I see a 1, I should go here. Okay, yeah, this is my simple construction. No? So if I see a 1, then I see a 0, then I see a 1, then I see a 1, then I see a 0, and then I see a 1. How many times did I see it? Final state encountered 2 times. But remember, this is not an EFA, this is a PFA. If at least one time I encounter a final state, it will be accepted. Hence, string accepted. But this is bad for the it should have been rejected, but it is getting accepted. You're seeing? So I'm not saying that therefore it is possible, it is not possible for PFA to not be constructed. This is just an example, right? How can you claim that PFA can never be constructed? Well, if you see a 101 and it should be accepted by the PFA, if you just consider the string 101, it should be accepted by the PFA because it's in the language. There is exactly one 101 block. But the fact that the PFA is accepting it means on reading 101, I have already encountered at least one final state. Correct. Now, if I move on from here, my number of final states will only increase. I've seen another 101 block, so it will only increase. So therefore, something like this will happen. I saw 2 final states. Therefore, for such a language, it is not possible to create a PFA. PFA is not possible. So therefore, there is a language L, this particular language, such that L is in EL, EFL, L is not in PFL. Okay. There are irregular languages which are not in P-regular, and any irregular language is a P-regular language. This is not the case. Okay. So yeah, please let me know. Any questions? Fine. Suresh, is it fine? Oh, sir. Okay. Okay. Sorry.
No, sir, it's fine.
Fine. Okay, Ankit, I've zoomed in. Okay. Please also let me know if you want me to go to a particular section. Okay, it's fine, right, Ankit? Let me know if you want me to repeat any argument. Okay, good. Fine. Okay, good. Okay, so okay, let's move on. Yeah, here's the question. Yeah, I think Suresh remembers this question well.
Yes, sir. Yes.
Yeah. Okay. So yeah, this question, number of possible languages over the alphabet A, B, C, D that can be recognized by a DFA with exactly one state. Okay. Here, yeah, last time when I mentioned it, I was saying I was talking about dummy states. Also, I gave this assumption that dummy states uh, are not mentioned, are not drawn. Okay, so this was the assumption, but since this assumption is not given in the question, we'll assume that dummy states need to be drawn. Okay, but um, how many states are we talking about? Exactly one state. So even if we draw a dummy state, we'll be increasing the size of the DFA. So we won't consider dummy states in this case. Okay. Now, okay. So if dummy states are required, then this is the answer. Okay. Um, so firstly, I can see two cases immediately. Okay. One case is when the state is a final state, okay, non-final state, let's say, and this is final. First case is when, okay, I'll increase the, okay, I cannot increase further. Yeah. So first case is when uh, the single state that I have, it's talking about one state, right, is a final state, is a non-final state, and the other one it is final state. If it is non-final, what kind of transitions can I have? Well, let's say I have A here. What is accepted by this DFA? What is the language of this DFA? There is no final state. So given any string, I will never land in a final state because f is defined as empty. So what is the language? The language is also empty here. Even if I make transitions on B, C, D, whatever, the language is still empty. Okay, so this is one possible language you can construct, the empty language, when it is a non-final state. Let's say it is a final state. Let's say it is a final state. Then what kind of things can you accept? Okay. Sorry. Then, so you could have accepted something like A, and so on, right? But since there are no dummy states allowed, so if I just write this, okay, then what is the language? Yeah, the language is A star. You will say, but what happened to B, C, D? Well, if dummy states are to be drawn, and this is a DFA, then B, C, D should be going to some dummy state, no? But then I'm increasing the size of the DFA that way. So it is not possible to have unused symbols. It is not possible to have unused symbols in your DFA if you want only a single state. Getting it? Because as soon as I enter, because if I don't want to use some symbols, I'll need to use a dead state. If I use a dead state, then I'll increase the size of the DFA. So B, C, D should also be used. So what is the language of this? What is the language? Well, it'll accept everything, right? It'll accept A star, B star, AB, ABC, ABCD star, epsilon also. So the language is sigma star. What is sigma for us? ABCD. This is all you can do with a single state DFA. So the answer is 2. Okay. Well, if you say that dummy states should not need not be mentioned. Okay. Oh, sorry. Right now we are not assuming this. But let's say you are to say dummy states need not be mentioned, then you can make a huge DFA. You can make a larger DFA, but I'm sorry, larger combinations for DFA. Okay. But in this case, it's only 2 combinations, so the answer is 2. Okay, let's move on. Let's do a similar thing. Okay, what are the number of possible languages over the alphabet ABCD that can be recognized with NFA this time, with exactly one state? Okay, let's see. Let's assume case state is a final state. This is my first case. Okay, state is a final state. Then here is what will be like. Okay, so this is one possibility. What is the language of this? It accepts only the empty string. Remember that dummy states, I don't need to worry about dummy states now because this is an NFA. If I don't have a transition for a particular symbol, it means I don't accept that symbol only. Next, this is the final state, and there is an A. What is the language? Well, the language is A star. Right, A, and so on, epsilon also. So similarly, if I have this, well, the language is B star. And then C, D. Okay, for C and for D. And then it'll have C star and D star respectively. Well, but I can have a combination of them, no? I can have something like A, B. What does it accept? L accepts A plus B star. Or A union B star, whatever you prefer. Similarly, I can even have something like A, B, C. L is A plus B plus C whole star. And similarly for D. So either I can list them out all for you. Let me list them out. Epsilon, A, B, C, D, A, B, B, A, B, C, C, D, D, A, and so on. A, B, C, A, B, D, B, D, E, and so on, and A, B, C, D. Right. But what is this? This is the, if I take them to be sets, okay, if I take A, B, C, D is my sigma, right? If I take this to be my sets, okay, a set containing only A, a set containing only B, a set containing only C, a set containing A and B, a set containing B and A, then what is this? This entire thing is the power set of sigma. This is the power set of this. Or in other words, it is a subset of all sets. And what is the count of the power set? How large is the power set? It is 2 to the power size of the set, which is 2 to the power size of alphabet for us, because sigma is the set of which power set we are interested in. This is nothing but power set, okay? Power set of sigma. And this is 2 to the 4, which is 16. Okay, so there are 16 different NFAs I can build. But in which case? In this case 1, when state is a final state. We are yet to see what if the state is not a final state. State is a non-final state. Then what will happen? This is what it looks like. And let's say I put an A here, and if I put a B here and here, this is a non-final state. C and D here and so on. No matter what, my L is always empty because there is no final state only. And NFA requires that at least one path should land to final state, but it's not possible to reach a final state only like this. So L is empty. And if you notice here, L does not appear empty language does not appear anywhere here. Okay. These are all non-empty languages. So it means this should also be counted. This should be added to my list of possibilities. So therefore, total number of languages you can generate is 16 in the case 1 and this empty language in the next case, which is total of 17 is the answer. Okay. Getting it? Fine, Ankit, is it fine?
Yes, sir. Yes, sir.
Okay, good. Yeah, I hope the rest are also fine with it. Akshay, Abdul.
Yes, sir.
Okay, good. Yeah. So, okay, yeah. So this one I had done it last time. Let's see how much time do I have. Oh, okay. So yeah, I had done this time, so I will not be dabbling into this. Okay. This.
Sir, do you
Yeah.
think the standard of assignment question is very tough?
Yeah. Yeah. What?
Do you think the standard of assignment question is tough?
Yeah. A few questions are. I agree, Suresh.
On the behalf of only lectures, we can't do it right.
Yeah. Yeah. What I would recommend is you take the standard textbooks and try to solve a few exercises. But it'll be worthwhile. I mean, you will really gain a deeper understanding when you
Yes, yes, sir.
try these kind of questions. No.
If somebody have not the deeper language, deeper knowledge, then it's difficult to solve all the questions. On
Yeah. Yeah.
behalf of only lectures.
Yeah. Only from the lectures it is difficult. You're saying, right?
Yes.
Yeah. Yeah. What I would say is, see, from what I analyzed in the assignment is around 80 to 90%. Okay, around 80 to 85% of the questions are doable, and
Yes, yes.
if you are careful enough, you are able to solve it.
Yes, yes.
I have noticed that 15%, 10 to 15% is where the problem is. So they are a bit difficult. Yeah, and sometimes quite difficult, quite challenging. For example, the first one I did was a bit challenging, right? The PFA, the what was
And
it?
last two questions was also tricky question.
Oh yeah, these two, right? Yeah, yeah.
Yes.
These are also tricky. But here, if you are careful enough, you won't make a mistake. But last time when I demonstrated it, I mean, I just wanted to give the slight idea, so I was not being too careful.
No issue, sir. Actually,
Yeah,
I
yeah.
asked this question. I asked this question from a person
Right,
who already teach this subject from 7 to 8 years.
right, right.
He also gave me the wrong.
Okay, okay, yeah, yeah, yeah. But if you are careful enough, then you will definitely get the answer in these. What I'm
That's
talking
why.
about is, yeah,
That's why I'm saying that the difficulty level of the question assignment question is difficult.
that's right, that's right, yeah. Or yeah, especially these questions are a bit more tougher. That's what I feel.
Yeah,
This,
for a BTech student, like it's difficult to score.
yeah, I
In
agree.
assignment.
Yeah, yeah.
Actually, I wrote this thing in feedback form because if you keep the standard of the question is very high, then it's difficult to get the certification. I think
Yeah, yeah. I definitely agree. That's there.
it
But
should be moderate. It should be moderate, not average, not tough, but it should be moderate question.
yeah, yeah, yeah. Yeah,
And,
agreed.
and conceptual question. These questions are like very difficult. You should have the deep knowledge. Then you will be able to do the all the assignment.
Yeah, yeah, yeah. That's there, Suresh. Hopefully, the instructors will see the feedback, and maybe bring changes in the assignments later.
Okay, sir.
Yeah.
Fine.
But in the meantime, I do recommend that you check out exercises from the textbook. Like, um, I mean, the Sipser itself has. So the course uses Michael Sipser, right?
Yeah, I'm referring that book.
Yeah. And if you want slightly tougher questions, then there is something called Kozen also.
Actually, I teach this subject in my fourth semester
Okay.
for BTech student,
Yeah, yeah. Oh, okay, okay.
and I thought that I will recommend to all the student to do the this course from NPTL.
Oh,
But
okay.
when I saw when I saw the assignments, then I don't do not recommended them
Yeah,
because they have no a time a lot of time to spend in
that is
three to
true.
4 hours from so regular
Mm-hmm.
basis, and they also not sincere about that because they have not of only one subject, right?
Yeah,
they
yeah.
have they have to read 6 to 7 subject in a semester.
That's right. That's right. Yeah, yeah.
When I saw the assignment, then I didn't recommend anyone.
Yeah, yeah. Especially, you need a lot of mathematical maturity also, right?
Yes. Okay, fine, sir.
Yeah,
Continue.
yeah, yeah, sure. So more than 6, 7 subjects.
Yeah.
Actually, yeah.
Ankit,
Oh, I
Ankit
have
is
11 subjects.
Ankit is Ankit is I think in BTech, right?
Oh, okay, okay. So which year are you in? Which semester, Ankit? BTech,
4 or 6
sixth
sem, right?
semester.
For which university or college, Ankit?
Sixth semester means third year.
Sir, I am from Chandigarh University, CSC department.
Okay,
Mm,
okay. Actually, sir, my funda is that
mm-hmm.
the subject which I taught in my in my timetable,
Yeah.
I joined that course from NPTL
Mm,
so that I can increase my knowledge, existing knowledge, so
mm,
can I can deliver the student
mm,
try to best.
mm.
I am working
That's
in
good.
assistant professor in Manipal University, Jaipur.
Oh, okay, nice, nice. That's good. That's good. And also, I mean, despite the assignments being tough, I hope that, but you are learning newer and newer concepts, right? I
Yes,
mean,
yes, that's why I joined. It is
yeah,
12 week
of course.
course,
Mm,
and I continue doing the assignment and attending the lectures.
mm.
Then I feel that no, I am not giving much more time. It's require more time also.
Yeah, yeah, yeah. Agreed.
Still I'm doing all the assignment, and I'm trying to get certificate. I will give the exam also.
Oh, that's nice. Thanks. But yeah, it's good that you are. I mean, doing it on not just for yourself, for your students also, right?
Yeah, yes.
Nice, nice. That's good, Suresh. Good luck for your exams also. I think it will be in what, May or June. Well,
It will, I think, April or May, I
oh,
think.
April. Okay.
Maybe, sir, maybe May.
Hmm. Yeah, I think it is May.
Yes, sir, 20th of May.
Okay, okay. Let's see. Yeah, hopefully, yeah, the exam will have a mix of. I don't think there will be just tough questions also. I think it'll be only, yeah, again, 10% of the questions may be toughest,
Yes.
right? Okay,
Okay, sir, fine, continue.
okay, yeah. Yeah, this one, please check the past videos, okay? Week 2. So please check out week 2 where I talk about NFAs and why reversals you can directly do on NFA, okay, and not on a DFA. Okay, uh, let's go next. Okay, here is a question. So, computation on binary vectors. So, yeah, for example, this one, try to interpret questions a bit differently. Okay, that is what the tip I give you. For example, in the previous one, the PFA one, we wanted to look at from a language theoretic point of view, like okay, this machine only accepts prefixes and so on. So here also, don't be intimidated by seeing all these vectors here. Okay, here we have sigma equals 1 0 0 1 1 1 and 0 0. So what does it mean? This means that this is your alphabet and these are your symbols. Okay. So if say A is 1 0, B is 0 1, C is 1 1, and D is 0 0, your sigma is A B C D. I mean, so you can interpret it this way also. So don't be intimidated by all these vectors. Okay. So what is S? Let S and these set of vectors A1, B1, A2, B2, and so on denote an arbitrary string. Okay. Since these are symbols for you, before we were dealing with A, B, C, D, 0, 0, 1, and so on, right? Similarly, this is one symbol, this is another symbol. Interpret it that way. So what is S? S is an arbitrary string. So it has this symbol, and so on. A list of symbols, a concatenation of symbols, right? Belongs to sigma star. Yeah, this belongs to sigma star. What does it mean? It means this belongs to this, the closure of this, the clean closure of this set, this alphabet, which means A1, B1, and so on take values from 0, 1. Okay, this means AI, BI are from 0, 1. Okay, now let BS denote the binary number generated by the string S. Okay, let BS denote the binary number generated by the string S. Now let L denote the following. So BS, okay, that I don't need to explain what binary is, right? We all know that. Let L denote the following. L is the set of all these strings, okay, string where each symbol is a vector, 0, 1 vector, where some condition is satisfied. Condition A is satisfied. Okay. L is all those S in sigma star. What is sigma? Sigma was that symbol, right? Vectors 0, 0, 0, 1, 1, 0, 1, 1. Okay. Such that some condition is satisfied. Condition A is satisfied. Now, select all the options on condition A that ensure the language L is regular. So what kind of conditions can you have so that L is resulting language L is regular? Let's see the first one. Condition A is B of A1, A2, A3, AN, and so on is greater than equal to B of B1, B2, B3, and so on. What does this B mean? This means the binary number. So if you have this, okay, if you have 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, this is your string. Okay, and top ones are A, if you see. Top ones are A and the bottom ones are B. Top ones are A and bottom ones are B. So top ones are A1, A2, A3, A4, and so on. And this is B1. Bottom ones are B2, B3, B4, B5, and so on. Okay. So in other words, A1 till A5 is 0, 1, 1, 0, 1, and B1 till B5 is 1, 0, 1, 1, 0. Now what are we saying? We are saying condition A is the binary of A1 to AN is greater than equal to the binary of B1 to BN. So this is already in binary. Okay. So how do you check whether one binary number is greater than the other or not? Well, if you recall, or it is kind of intuitive also, you go from left to right and find out who has the most significant bit which is greater. Okay, so you go from left to right. Okay, so let's say you go from left. Let's say okay, let's say this is 0. Okay, yeah, okay. Now let's say you go from left to right. Okay, 0 compare with 0. No. 1 compare with 0. Oh, okay. This one has a MSB greater than this one. So this is the greater one. This binary number is greater than this binary number. A simple algorithm, right? But using DFA, you need to figure it out. And these are your symbols. Okay. So what kind of symbols are good for you? If you see a binary on moving from left to right, if you see a 1, 0, this is good for you. As soon as you see a 1, 0 moving from left to right on the string, it means as soon as you see a 1, 0 moving from left to right, for example, 0, 0, no, 1, 0, okay, I saw a 1, 0. It means this one is greater than, and my language should accept. My language should accept if the left side, that is A1 to AK, is greater, right? So I'll construct the DFA now. So this is my start state. Okay. As long as I see 0, 0, I'm not interested. As long as I see 0, 1, okay, not 0, 1. If I see 1, 1, I'm not interested. As soon as I see a 1, 0, it means that A is greater than B. The top part, binary of top part, is greater than the bottom part, binary of bottom part, interpreted as binary. Then I should accept. Oh. No matter what, 0, 0. Okay, let me just write sigma. For all sigma, okay, it's good for me. Now, if I see a 0, 1, it means the bottom part, okay, the most significant bit of the bottom part is greater than the corresponding bit in the top part. So my string should get rejected. So this is a dead state. Fine. So yeah, I hope that is clear. If you want to test with a string also, it's okay. So for example, this string should get accepted because the top part, the binary top part, is greater than the binary bottom part. So let's see, 0, 0, it will stay here. 1, 0, next vector is 1, 0. So you will move to this and it will keep staying here. Whatever comes, it will keep staying here because of the self loop, and you will get accepted. So yeah, rest, okay, yeah. So condition A, this is true. Next, equality. So B, binary of this is equal to binary of that. Very similar, very similar. Let's try B. Binary of this is equal to binary of that. What is an example? Example is 0, 0, 1, 0, 1 is same as 0, 0, 1, 0, 1. Whatever is at the top is same as whatever is at the bottom. In other words, string only has 0, 0 and 1, 1. Because as soon as you see a 1, 0 or 0, 1, it means either the top and bottom don't match. So the binary equivalent doesn't match. So it's simple. Just make a state here. Okay. And if you see okay, if you keep seeing 0, 0 or 1, 1, it means the binary values are equal so far. But as soon as you see a 1, 0 or a 1, 1, 0, 1, you reject it. Okay, and this is the final state. Okay, so for B also you can construct a DFA for equality. Now for C, is this condition true? S is 1 by 0 to the P, 0 to the 1 to the 0, 1 to the P for some P greater than or equal to 0. Well, 0 and 1 are symbols here, no? This vectors 1, 0 and 0, 1 are just symbols here. So even if you take 1, 0 as A and 0, 1 as B, it's nothing but A to the P, B to the P. Right? But this is non-regular. We've seen this language enough times and we know that this is non-regular. By pumping lemma also you can prove that this is non-regular. So this is clearly not possible. Okay. Yeah, so the final one. Now the final one is a bit tricky, but if you've understood the first three, then you'll definitely understand the final one, the max. Actually, it's not even tricky. It's just I won't draw the entire DFA. I'll just tell you the general idea, and you will understand why it's possible to make a DFA for this. Or yeah, okay. So the question says max of A1, A2, and so on till AN is greater than or equal to the max of B1, B2, and so on till Bn. Right. How do you solve this? And so what it means, it's like, see, A1, A2, and so on till An, and below I'll have B1, B2, and so on till Bn. So this is what it'll look like. Now the top part, the maximum of the top part is greater than the maximum of the bottom part, which means if I see a 1 anywhere on the top, then it is guaranteed to be greater than or equal to the maximum of the bottom, because even in the bottom there's only 0 and 1. So even if the maximum is 1, 1 is greater than or equal to 1. So this is good, except if the top part, okay, getting it? If the top part, there is at least one symbol there, I'll accept. Next, okay, next, what kind of things can I accept? If the top part is, now there is no 1 on top, okay, this is case 1. Case 2 is 1 does not belong to A1, A2, and so on, An. What does it mean? It means A1, A2, and so on till An are all zeros. Because we said that there are no ones in the top part. So if all of A1 to A2 and so on, these are zeros, when will this condition be true? This condition will only be true when all B1, B2, and so on are also zeros. Because even if one of them becomes 1, the maximum will then come out as 1. But here, since all are 0, the maximum is 0. So 0 is greater than or equal to 1. No. So to satisfy the condition, even B1 to Bn should be, this means even B1 to Bn should be equal to all zeros according to condition 1. Getting it? Therefore, let's take these cases and make our final DFA. here, yeah, here's the final DFA. If I keep seeing 1 on top, either 1 0 or 1 1, I'm good. I'm in the final state. Okay. If I keep seeing top, if if 1 does not appear in any of them. Oh, okay, sorry. As soon as I see a 1, okay, even one, even a single 1 is enough. Okay. If I see a 1 0 or 1 1, then I can accept it. Even if I see a single 1 on the top. But see, this is not the case. I keep seeing zeros. If I keep seeing zeros, I should also keep seeing zeros on the bottom. So what does it mean? If I see 0 0 and I keep seeing 0 0 on both top and bottom, then I should accept. Otherwise, I'll just keep waiting. What are the remaining cases? 0 1 and 0. Yeah, just 0. Okay, this is my final DFA. Okay, so is it fine?
Yes, sir.
Okay. Okay, so I think it's fine for others also. So yeah, with that we've come to the end of the first part. We don't have enough time, so I'll try to cover. Let's see. Maybe we won't be able to do all the questions in the remaining part. Okay, so we've done all the assignment questions for assignment 1 and assignment 2. Next time we'll do 3 and 4 maybe. Let's see. Okay. Yeah. So here's a simple question. So for the new week part, okay. So this is based on CFLs and Chomsky normal form. So which of the following are true about CFLs? Statement 1 is there are CFLs that cannot be generated by grammars in Chomsky normal form. Statement 2 is CFLs are closed under complement. Statement 3 is CFLs are closed under intersection but not union. So any guesses? Just statement 1, statement 2 only, statement 1 and 2, statement 2 and 3. Okay. So statement 1. There are CFLs that cannot be generated by grammars in Chomsky normal form. This is clearly oh, okay, I see why the silence is there. Okay. So let's say there is an option E. Okay. Yeah.
One should be correct, sir. Statement 1.
Statement 1 should be correct. There are CFLs that cannot be generated by grammars in Chomsky normal form. Why? Is there an example for that? One should. Why is statement 1 false? Okay, because we know that we can always make Chomsky normal form for every grammar without affecting the language it computes. Right? Given a CFG, I can always convert it into a Chomsky normal form, and it will not affect the language that this CFG was generating.
Yes, yes, it's true.
Right? And CFG is exactly all the it is the grammar for all the CFLs. So again, yeah, CFL, CNF. For every CFL, you can have so for every CFL, you can have its grammar in CNF, Chomsky normal form. Okay. So therefore, we are saying it cannot be done. So therefore, statement 1 is false.
Yes, yes, yes.
Okay. Now let's look at statement 2. CFLs are closed under complement. This is from the closure properties that CFLs are not closed
Under
under complement, right? Because if they were closed, then it has some consequences. It's there in the lecture, I think. Now, final statement 3 is CFLs are closed under intersection but not union. Statement 3 is supposed to be the exact opposite of the statement. CFL are closed under union but not under intersection. Closed under union, not under intersection. Okay. So therefore, answer is that all of them are false and E is the answer. I'm sorry for not revealing E in the beginning. I didn't realize there was a mistake in the question. So yeah, in fact, if you remember, then complement is actually proved by this closure thing, because A complement union B complement whole complement by De Morgan's law is A intersection B. So union between CFLs is closed. So union of CFLs is CFLs, right?
So statement 3 is true, na?
Statement 3 is not true.
No, not true, not true, not true.
Yeah,
Right, right. Because
it,
CFL closed under union.
exactly, but
Yes.
not closed under intersection.
But here it is, but not.
Hmm.
Okay.
Opposite,
Yes, yes, yes.
right?
Fine.
Yeah. Okay, let's look at this one. Quick one. Say a word apple is accepted by a grammar in Chomsky normal form. How many steps of derivations does it take to accept the word? Okay. So here is a fact. Okay. It was there in the lectures also. It's a well-known fact that any CNF to generate a word of length n requires exactly 2n minus 1 steps of derivation. So here, what is n? N is the length of A, P, P, L, E, which is 5, which means 2 times 5 minus 1, which is equal to 19 steps of derivation. I think the proof was given as exercise there. Right. We can even try it. Let's say, what is Chomsky normal form? Chomsky normal form is of this form. A gives BC and D gives A. These kind of uh, variable followed by two variables at the right hand side, a variable in the left hand side, and one symbol. Only these kind of production rules are allowed. So a start state gives something like BC, and BC will give DEC, because B was what I expanded, and DEC will give F, G, E, C, and F I'll expand will give, and so on. You keep doing this, and
Sir, how
yeah,
sir how DEC is expanded from BC?
yeah. So I'm just implicitly assuming that okay, this is only for show. Okay, this is what I'm saying, that CNF applies this kind of graph. D gives FG. That's what I'm assuming.
Okay.
Okay, because in Chomsky normal form only this or this is allowed. No, right? Chomsky normal form.
Okay, fine.
Yeah, exactly. Two variables on the right or one constant on the right is allowed in any production. Correct. Yeah, and then, oh sorry, not 19 steps. What am I doing? 9 steps. Yeah, 9 steps. Should require 9 steps. So FGEC. Then let's say F generates some FGH HIGEC. Let's say this, and then H generates AIGEC, and I generates PGEC, and G generates PEC, and E generates LC, and this generates E, apple. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is another way to come to the answer. Because these are the only type of derivations possible. Okay. But this is something special about Chomsky normal form. You'll require at most 9 steps. Sorry, 2n minus 1 steps for a string of length n. Okay. So answer is B, 9. Okay, it's 7:46. So the remaining will take time, especially the fifth question will take a lot of time. So I think we'll break here then. Okay.
Sir, but please take fifth question on next turn, sir.
On
Fifth question.
do it right now, you mean?
No, on next turn, because
Oh, sure,
at
sure.
present we have no more time.
Okay, okay. It's okay. We have barely 13 minutes. 13 minutes. Or I could have done it right now, but okay, I'll do it next time.
Yeah, sir.
Okay,
No issue.
okay. Okay, we've come to the end of the session. Any questions?
No, sir. Thanks.
All right. Okay. Akshay, Abdul, any questions?
No, sir.
Okay. Okay, Abdul also, no questions, right? Okay. Okay, then we've come to the end of the session. Next session. Okay, yeah. About next session, it will be held on Saturday instead of not this Saturday. Okay, not this week Saturday. The next Saturday instead of Tuesdays. Okay, only for the
Means
next week. Only for week.
2
Yeah.
of second March. Second March.
Yeah. Let me check. Uh, that's right, Suresh. It'll be 2nd March.
Okay.
So next next problem session will be on the 2nd of March, week 5. Okay, only for that day, and the timing is. Okay, please wait for a while. I'll check the timing. Should be it's either 5 or 6. Let me see. Six to eight, yeah. 6 to 8. There is another session at 3 to 4 or something, but that is not mine. Okay. I mean, it depends on you which session you want to attend. Both are problem solving sessions only. But I will not be conducting it. I'll be conducting the 6 to 8 slot. 6 p.m. to 8 p.m. on Saturday, 2nd of March. Okay, then. Yeah, that's it.
Okay, sir. Thank you.
Okay, thank you, Suresh.
Bye, sir.
Okay. Okay. Bye. Good night, guys.
Thank you, sir. Bye, sir. Good night.
Okay, good night, Akshay. Bye.